All right, so today we're going to be looking at databases. But last time there was a question about threading and what is a thread and multi-threadedness. And so I thought that it deserved a little bit of a more substantial answer. And so I wanted to just give you a little bit of a demonstration today. First of all, this is the best image that I found on a Google image search of a thread versus a program and stuff like that. And so it just gives you an idea that there are multiple, that you have one program where you have multiple threads running within that program at the same time. You can do that. Now, everything that you've done up to this point has been a single threaded process where you've got one program, one thread. Let me make sure that, yep, it's working. So you can take that off. All right, so, but you can also have a program that launches multiple threads. You can actually have a program that launches another program, right? That's what an operating system does. But when a program launches a copy of itself, then that's called forking. That's not something that I'll demonstrate today, but that is another possibility. And then you have these independent programs that can talk to each other if you want them to through what's called inter-process communication. Now, a thread is a little bit more lightweight in that you only have one program, right, where there's shared data, shared code, and shared files, but each one of them has their own call stack. So it's like an independent program that's running independent of each other, and they can talk to each other, but they can talk to each other much more efficiently without having to go through the operating system. They can work independently, not stepping on each other's toes, but you do have to be careful because if there's shared data and one thread is working on that data and another thread is working on that data, then they will potentially step on each other's toes. But the advantage here is that each thread can run on one processor. Now, if you've got a really old computer where there's one processor and there's one core on that processor, then there's no point in multi-threadedness at all because only one thread can ever execute at the same time. But if you're on a modern computer, Intel Duo, right, you've got 2 cores, quad cores, however many cores you have on a modern processor, then you can run multiple threads at the same time. Now I'm going to give a demonstration of why that is potentially a huge thing for as far as the processing power goes. First of all, I want to show you another program here. So I've got a program here that's do nothing. Right? Let's look at that really quick. Do nothing.c. It's all in C here. I've got Java examples here too that I've used before. But anyway, all the program does is print out hello. Right? It's flushing the standard output so that it actually prints instead of waiting. And then it goes to sleep for 10 seconds. In other words, it does nothing, just like it says on the tin here. Do nothing for 10 seconds. Then it wakes up and it says hello and then terminates. So let me go ahead and run this program. Do nothing. Right? And if we sit here and wait for 10 seconds, of course, it'll eventually say world and then end its execution. While we're waiting on that, I'm going to go ahead and log in to the same, I'm on the CSE server right now, the same system here, and I'm going to go ahead and launch HTOP. This is a way that we can monitor what processes are currently running. And you'll see here that there are 64 cores on the CSE server. Right? That's a pretty beefy server. Even your modern laptops, though, are going to have, I think this one is an i9. It's going to have, it's a Mac i9, and I think that it has maybe 8 cores. I'm not sure. Anyway, it doesn't really matter. I'm using the CSE server here. And you can see that some of these cores are running, like core 23 here is running at 100%. Core 45 here is running at 100%. Some of the other cores are idle. In other words, there's nothing running at that particular moment. Sometimes there's a little bit of a process that's running. It's only 3.8% busy. Okay. So what I'm going to do is go back over here and I'm going to launch 5 of these things. I'm going to launch them in the background. It's probably not going to show up here in the monitor because it doesn't do anything, right? So it's going to be using 0% for the entire time. But I'll go ahead and launch 5 of them. 1, 2, 3, 4, 5. And if I list all of the processes that are currently running in my current shell, I see the 5 copies of this a.out. Right there, the first one, second one, third one, fifth one, they all got done, right? But I was running the same program at the same time. That's not threadedness. That is one program, two programs, five programs running at the same time, but they were running on different processors. What I'm going to do now, if you wanted to make these not do nothing and do something and talk to each other, you could. What I'm going to do now is show you what multi-threadedness looks like. Before we do that, though, I'm going to lay the groundwork for what this demonstration is actually doing. So let me go ahead and open up, where is it? Count primes. There we go. All this is going to, first of all, I've got a function here. You've probably seen this before, where given x, it says whether or not it's prime. A prime number like 2, 3, 5, 7, 11, right? That's only divisible by itself in 1. Otherwise, if it's composite like 4, that's because it's 2 times 2, right? What we're going to do is we're going to count the number of primes, and we're going to time how long this program takes. We're going to take in n. The number. So if I say 1,000, I want to know how many primes there are between 1 and 1,000. I want you to count up how many there are. All it's going to do is go through a for loop here and ask if it's prime. Go ahead and increment this counter. Right? It does this through. This is basically the kind of like the sieve of Eratosthenes, if you've ever heard of that. It's a brute force method. It is very inefficient, and it's inefficient on purpose because I want this program to actually run and do something. But I time it when we start. I time it when it's done. I report the number of primes, and I report the computation time as well. Okay. So let's go ahead and run this program and see that it's actually correct. First of all, count primes.c. Oops, I need to include the math library on this one. There we go. And that's good enough. So a.out, of course, I need to put in n. So if I put in 1,000, it'll tell me that there are 168 primes between 1 and 1,000. Right? You can go ahead and verify this if you want to on Wolfram Alpha. And ask, how many primes are there less than 1,000? How many primes less than 1,000? 1,000 itself, of course, is even, so it's not a prime number. So I don't have to worry about that. 168, great. My program seems to work. Now, if I went and did this for, I don't know, 10,000, I still get a reasonably fast answer, right? If I did this for, let's see, 1 million, right? It's still reasonably fast. 10 million? 1, 2, 3, 4. Should only be about 10 seconds or so. Yeah, 7 seconds there, right? I'm going to go ahead and bump it up to 16 million here. 16 million should be in the neighborhood of around 10 seconds, which is why I chose 10 seconds for do nothing, because it's going to be about the same thing, right? But let's go ahead and ask Wolfram Alpha while we're waiting here. What did I put in? 16 million? 6, 1, 2, 1, 2, 3. Right? Just to verify that it's actually working, and that's 121, 127. Oh, wait. Did I not put that in correct? 16 million, sorry. 16 million, there we go. I forgot a 0. All right, so 1031130. Great. My program is working, but it's really inefficient, right? 10 seconds, 11.8 seconds in this case. If I ran it, I'd get a slightly different time because, of course, there's context switching. My program is not running fully the entire time. Sometimes it's going to sleep for other processes, excuse me. But it's probably that one on processor 4 right there because I just launched it. In fact, it's green, so it's probably mine. Right? Some other people are running some really intensive stuff. Well, at least one other person is running really intensive stuff on here right now. But there, it's done. There we go. It got done, so it disappeared from processor 4. Okay. So what if I farmed this out to 2 processors instead? What if I said the first processor or the first thread, you count the number of primes from 0 up to 8 million. And then the second one, you count the number of primes from 8,000,001 all the way up to 16 million. Right? I'm dividing the work in half. And I'm saying you take this half and you take this half. If you did this in real life, right? If you said that there's this wood that needs to be chopped, right? Person A, you go ahead and chop this this pile. Person B, you go ahead and chop this pile. Assuming that the 2 people worked at the same rate and didn't tire or anything like that, you'd get done in what? Half the time? If it took you 1 hour to do it with one person, clearly it would take you 30 minutes to do it with 2 people, right? Well, what happens if you set 4 people to that task? Now we're down to 15 minutes, right? 1/4 the time. What if you set 8 people to that task? Now you're down to 7.5 minutes. You can get it down as much as you want. Now, at some point, of course, you run out of people, or in terms of computing, you run out of processes or processors, right? It would not make sense to divide this among 128 processors. Why? I only have 64, right? So even if I divided it up into 128 processes or threads, only 64 of them can run at one time. What are the other 64 doing? Right? They're waiting, right? It's like splitting up all that firewood chopping, but only having 64 axes and 128 people, right? 2 people can't use the same axe at the same time. Likewise, 2 processors or 2 threads cannot run at the same time unless you have a processor by itself. So let's go ahead and take a look at an alternative here. I'll go ahead and look at the count primes threaded. Now don't worry about the details here because I'm not going to get into P threads or anything like that. P threads stands for POSIX threads, I believe. But in any case, let's take a look at how I'm dividing up the work here. So I take in n, as I did before. You want to count the number of primes up to and including n. But I also ask you, how many threads do you want? Right? If you want 1 thread, that was the first demonstration I gave, and it'll take about 12 seconds. If you want 2 threads, it'll take roughly half the time. 4 threads, 1/4 of the time, roughly. Of course, there are diminishing returns here. The way that I do it is by splitting it up. Right? I set this thread data to, you take the first, if n is 16 million and the number of threads is 16, then each one of you gets 1 million integers to count up, to test if they're prime and then count up, increment a counter if they do. What I do then is I start a clock. I launch all those threads by creating them, and then I have to make sure that the entire program doesn't die before everybody gets done. The main program up here, and I've closed the picture that I had before, but the main thread, if it launches all these other threads, then it has to know, okay, when these 4 different threads are done, I'm going to take each result from each one of them and I'm going to sum them up. That's what I do down here with the result. But I have to wait for all 4 of them to be done. I can't wait for the first and the third one to be done, and then, oh, well, I could add those up, but I'm still waiting on the second and the fourth one to be done. So I'm going to wait for all of them. That's called blocking. I'm going to block the main thread until all the other threads are done with their work, and then I'll go ahead and add them up, report the result. Right? So let's go ahead and take a look at this. And I'm reporting 2 different times here, and you'll find out why here in a second. So count primes threaded. Oh, I need to include the math library, and I also need to include the thread library now too. But once I've done that, you want to go a.out. I don't know what that null is there. That's just my mistake. Let's start out with 16 million. 1, 2, 3, 1, 2, 3. Right? Since we know the answer to that, and we also have a benchmark, it took about 10, 12 seconds before. And let's try it with 1 thread to begin with. When we do this, we create thread 001, and it's searching from 0 up to 16 million. Right? And there's only 1 thread, so they've got to chop all the wood. And it's going to take that full 10, 15 seconds, whatever it was. There we go. It took 15 seconds this time. The actual time was about 16 seconds. Right? This was processing time. It adds up. And we'll see that. See here in a second what I mean by that. But of course, I get the same answer. Now, if I went with 2 threads and divided that in half, it would only take about, what, 5, 7 seconds or so? Something like that. The first one takes 0 to up to 8 million. The second one takes 8 million up to 16 million. And then we add them up together. The first thread reported this many primes. The second thread reported this many primes. We added them all up to get the original result. Now the computation time seems to be the same here. Oh, wait, did I screw up? Nope. The computation time is the same, but now the actual time has gone down. That's what I need to be looking at there, right? It's not exactly in half because you are paying for the cost of generating these threads and to run them and all that other stuff. So it's not exactly 50%, right? Let's go ahead and bump it up to 4 though. 1, 2, 3. There, 2 of them got done, third got one done. Now we're down to 5 seconds, right? Before, what was it, 12 seconds? So I cut that time roughly in half. But the actual computation time is still the same. Why? 4 threads operating in 1/4 the time, you still add up all those, all 4 of those to get the actual computation time, right? 1 second on processor 1, 2 seconds on processor 2, 1 second on processor 3, 4 seconds on processor 4. You still have to add all those up for the actual computation time. If you keep going, of course, it's going to get faster and faster and faster, right? Now, it only took 2 seconds. If I divide this up into 16 processes, 1 second. What if I go up to 32? Right? And you see that there was a really quick burst of energy up there of up to 32 processors being taken. But if I go up to 64, probably the diminishing returns, right? Actual time is way less than 1 second, but the processing time is actually going up because of the cost of doing this, right? But the actual real time is going down. If I tried this with 128, right? There's really no difference there. But you saw, oh, did you see the flash up there? Nope. It's a little bit of delayed flash that I'm using all these things. Let's go ahead and bump it back down to 16, but let's go ahead and make sure that it runs for a little bit longer so that we can actually see it. I don't know, 64 million, right? 4 times as big. Right. I don't even know if this, one of them got done. There we go. Now we can start seeing that I'm grabbing like 16 processors. There, it's all done. But I was grabbing more and more processors, right? Now, if I'm grabbing processors, that means that other people can't have those, and so I'm being greedy here. Let's go ahead and try with 32, but let's bump this up to 128 million. There we go. There we go. Now the server is burning downstairs over in Avery. 100% on a whole bunch of. I'm not. It's not giving me all. What did I ask for? 32 or 64? Yeah, it's not giving me all 32 at the same time. You're too greedy, right? But that's the power. In fact, wow, computation time blew up there, right? But the actual time is much less than if you did this with just 1 thread. So hopefully that's a good introduction to the ideas. Right? If you want to explore more, read about a tutorial about p-threads in C. I can provide this code if you're interested, and you can play around with it. Do not try to do any threading for your project, right? Unless you get the entire project done and it's working, then you can try to modify it if you want to thread it. Okay. There are lots of issues, by the way, that go along with multi-threaded environments. Everything has to be thread safe. You have to have mutexes. You have race conditions where one thread needs something, another thread needs something, but it's always it's always preempting another thread. And so you've got all these issues that you have to be aware of before you can write a thread safe program, right? But otherwise, there we go. All right. Don't need that anymore either. Questions? Multi-threaded environments? So it's said that we now live in a multi-threaded world, so you do, some people even advocating doing it from the beginning. It requires a hell of a lot more experience, though, and concepts to get multi-threaded down well. Right? Anyway, so on to databases. This is not going to be a full introduction to databases. If you take Computer Science 2 next semester, you will get a full introduction to databases where you'll design a database, you'll learn SQL, you will go through the process of database connectivity, writing a program to connect to a database and pull data, process data. You'll get a little bit of exposure to that in your lab next week, Lab 15. We've already designed the database. We've already written the code to connect to the database. All you have to do is enter your favorite video games and then generate a report of those video games. We'll see that here in a second. But otherwise, data is fundamental, right? In C, we've been focusing on 3 basic data types: integers, doubles, and strings, or char stars. We've then extended that when we realized that there are pieces of data that you need to model in the real world that are made up of multiple pieces of data. Students have a first name and a last name and a social security number and a GPA. Airports have a name, a GPS ID, a latitude, longitude, etc. You need a way to bring all those things together into one logical unit. And then you need a way to define relationships between those two things. We didn't do this, strictly speaking, we didn't do this, but you can imagine, well, we did this. When we did, what did we do? Films, right? We created a film structure. We took another step and we separated out the person who stars in that film or who directs that film. We separated out those two things because they were different entities. And then we also separated out the birth date or something like that, right? What we were doing was we were normalizing that data. If I had taken all of those pieces of data and treated them as one unit, right, then that's what's called a flat file. That's what a table typically looks like. Here's a table of computer science books associated with a course, associated with a title, author, topics, and a URL. This is a flattened data model because an author is separate from the book that they wrote. They could write many books, right? One author can write 10 books. One book can have multiple authors. So if you want to normalize this data, you need to separate it out into two logical units. Unfortunately, the data representations that we've seen so far this semester are all flat. Here's one data representation of the exact same data. What is this called? You should be working with this in your Hack 15 right now. It's CSV, right? It is comma separated values. Instead of a nicely intended for human readable consumption, here we've got an HTML table. Here, this is intended for CSV processing, where you separate each token, the same tokens as over here, into, you separate them by using a comma. Here's the same thing in a different data model. This is JSON. This is a JavaScript object notation. And it separates things into things that look kind of like structures, and that's basically what they are. They're data containers with key value pairs. Over here, we just assume that the first token is associated with the course. The second token is associated with the title, etc. Over here, that's a little bit stronger association because it's repeated for each object. Objects are separated by commas. Keys and values are separated by colons. Right? And then each key value pair is separated by a comma here as well. Okay? Here's another representation of the same exact data. This is XML. This is extensible markup language, where you've got a hierarchical nature here. You've got a root element here called books, and inside that you've got these tags called, this is the first book. That's where the first book ends. Here's where the second book begins. Here's where the second book ends, etc. And each one of these pieces of data is marked up with a tag, an XML tag. This is very similar to HTML. In fact, HTML is a subset of XML. All right? HTML5 is a new thing that everything's HTML5 now, right? XML is HTML5. Anyway, I think, don't quote me on that. Anyway, this is a way to represent data as well. All three of these, however, are flat. There's no separation between the two logical units, an author and their books. Right? And that leads to a lot of repeated data. If I wrote 3 different books in this, let's just take courses. There are 3 books associated with this course. This is a different course. There's only 1 book associated with this course, 155E. There are 3 books associated with 155T. Now, every time a book is associated with that course, this data is repeated over and over and over again in all 3 data representations. Right? That redundancy can lead to failure points and data anomalies. For example, what if I came over here and misspelled CSE 155A, an older course, right? Logically, these are still the same course, but because I had repeated data, I had a potential to screw it up, right? Whereas if this were one thing, one unit in a table, in a database, then there would only be one reference to the actual course title, right? and there'd only be one potential failure point. If I change the name of that course in one record, then that would be changed for all the associated records as well. And that's where relational database management systems come in, right? Also, programs are short-lived. They're ephemeral, right? We need data to persist, to be saved from one run of a program to another run of the program. And we call that persistence, right? It persists. It's just a fancy word for saving data. Don't worry about it. Each one of these are falling short. They're all flat data models. To find a particular record would require you to process the entire file. There's no easy way for multiple programs, multi-threaded programs, to access the same data because you might have file locks on it. If one thread comes in and changes the data, this other thread is blocked from even reading the data, even if it's not going to change the data, until this thread over here has saved the data, right? Unfortunately, that means that you have very, very inefficient programs. There's no format enforcement. There's repetition of data. There's data integrity issues, right? There's nothing to stop me. Well, let's see. I don't have any numerical data here. But if I had a numerical data, like say number of pages, so num pages, right? I could say hello, right? Num pages, right? Now, is that correct data? It's not a number, right? There's no way to enforce that when everything is just text. So the solution is an RDBMS, a Relational Database Management System, where data is stored in tables. Now, you might immediately think Excel. Excel, yeah, you've got tables, and you've got what look like tables in Excel, where each table has columns, data, and then records, rows. But an Excel file is a spreadsheet. It is not a database. If you were looking for the Microsoft Office analog of databases, you'd be looking at MS Access, where you can relate one object in one table to another object in a different table. You can do that somewhat with Excel, but it's not a true database. Right? Each table has rows and columns. The rows represent single records. Columns represent the data stored in that record. So for example, if I wanted an author and a book relationship, I would separate those out into two different tables so that each author only has one record associated with them. Each book only has one record associated with them. And to represent that this author wrote this book, I would have a relationship between those two tables somehow. That's where the relational database management system comes in. There are several types of relations. There's a one-to-many relation, where one record can be associated with many records over in this table. Right? There's a many-to-one relation, which is what? Well, it's the same relation, but in reverse. Right? So you're changing your perspective. If you're going from table A to table B, it's one-to-many. If you're going from table B to table A, it's many-to-one. You can also have many-to-many relationships, right? Where one author can write multiple books, and one book can be authored by multiple authors. Right? So maybe that's how the relationship that you want to model. Let's see. Yep, good. So in an RDBMS, records are identified generally with a primary key, and then you associate them together with foreign keys. Right? A key is basically just a unique identifier. And so you have a unique identifier over here. And who wrote this book? Okay, well, that's a foreign key back to this key, a primary key over here that's associated with them. You can also have constraints and data enforcement. Data storage can be done now, and the database management system handles multiple programs accessing the same data at the same time, making sure that they're not stepping on each other's toes somehow. Right? Those are the ACID principles that we'll talk about here in a second. It provides security, right? You can say that this user is allowed access to this table, but not this table over here. This user is allowed access to all of these tables over here. This user is allowed access to this column in this one table, but nothing else, right? You can have very fine-grained control on your security on the data. You can enforce data integrity by defining relationships and saying that this column has to be an integer. Attempts to insert data that is not an integer would be an error, and the database system would throw that back at you. Right? You can have constraints here, that an author's name is last name is required. So if you try to enter in an author record without a last name, then it'll reject that data as bad data. You can have multiple users, parallel access, et cetera, et cetera. All the problems of a flat file or file I/O are now solved. Right? And it gives you the ACID principles. ACID stands for atomicity, consistency, isolation, and durability. Atomicity simply means that every interaction with the database is called a transaction. Transactions are atomic. It's an all or nothing thing. So if you have a transaction that inserts record A, B, and C, but record C fails for some reason, for some constraint, it's like the first two never happened. It's an all or nothing thing. It'll roll back that transaction as if nothing ever happened. You have consistency. The database will always remain in a consistent state before and after a transaction. So if you've got a bunch of rules, database rules that you've defined that the last name has to be there, that a book can't exist without an author. If you've got those rules there, they will always be followed. There is a guarantee on that. It's consistent. Now, it could be inconsistent inside of a transaction, but before that transaction and after that transaction, the consistency is guaranteed. That's what a relational database management system does for you. You have isolation, that no transaction will step on the toes of another transaction. If you have transaction A, B, and C, they each basically get their own view of the database and they won't step on each other's toes. Only after, if this transaction starts after the end of this transaction, it will see the changes or updates that this transaction made. Right? It won't be in an intermediate state of some sort. And finally, durability, that once a transaction is committed, it remains so. So if there's a fatal error, somebody kicks out the power cord to your database or something, your server, and you bring it back up after you've plugged it back in, then it will be returned back to a consistent state. You might have lost some data that was in between a transaction, but whatever the last transaction that was committed and successful, it'll return to that state. Right? Lots of nice principles here. Another acronym. So we've got a lot of acronyms here, alphabet soup. Database management systems also provide basic access through CRUD. Create, retrieve, update, and destroy. Those are the four basic operations to data. Creating new records, retrieving records that have already been created, updating existing records, and then deleting records if you want. Right? Those are the four basic things that you can do with any piece of data. You want to insert a new record, great. If you want to pull data out of the database. If you weren't able to pull data out of the database, then it's kind of useless, right? It just goes down the black hole, right? And it's gone forever. So you need a way to retrieve stuff. You need a way to possibly update data if it changes. Somebody changes their name, or there's a new book and it wasn't written by that. I made a mistake. It wasn't written by that author. It was written by that author. I need to change that. Destroying records, you can just remove records if you want. Okay. So with the remainder of our time here, what I want to do is give you a preview of your lab. Right. So here's a database that's been designed for your lab next week. This is lab 15, the last lab. All right. What kind of relationships do you see here? Well, I see 4 tables first of all. Right. Let's focus on one table here first, the game table. What pieces of data are in that table? I see a game ID with this nice little thing to the left of it. Does anybody squint and see what that looks like? It's a yellow key, exactly. That's a primary key, and it's an integer. Every game is uniquely identified with this primary key. Generally, you want databases to take care of that for you. And good databases, you can configure a database to always generate a unique key. Right? If it needs to insert a new record, you say, all right, you go ahead and generate that key and let the database do its job. It's good at that. Right? You have the name of the game. You have a publisher. Right? But the publisher here is this little pink thing, or red. Right? What is a publisher? Think about the real world. What is a publisher? A person, if it's an indie game, or a company, right? Or multiple companies, if they've, developer and publisher B and publishing house or whatever, right? You can have a big giant corporation with 50 different development studios below it, right? And then they take credit and all the money for it. Exactly. And then or they punt it off to another publisher and say, you go ahead and make the 20th anniversary edition, and it totally sucks, right? GTA, right? Punt that off to a different publisher. Upscaling graphics are terrible. Anyway, you've got a publisher, and what is a publisher? Well, in this case, I've decided to model a publisher simply as a unique ID, right? That's also a key here, and then the name of the publisher. Imagine if I put these two tables into one table and flattened that data model. What would it look like? Rockstar Games, Rockstar Games, Rockstar Games, Rockstar Games, GTA 1, 2, 3, 4, right? I would have multiple records all with the same data. Repetition, redundancy, right? I want to remove redundancy so that if I make a mistake and misspell Rockstar Games, it is Rockstar, right? Okay, Rockstar Games, that I go in and I only have to change one record, right? And so there's a relationship between these two tables. What is that relationship that I've modeled here? Now, in general, in the real world, publishers can publish multiple games, and one game can have multiple publishers, but that's not what I modeled here. What did I model? This chicken foot over here, right, is a many relation. This is a one, so it's a one-to-many relation. One publisher can publish multiple games. But one game only has one publisher. I chose to simplify the model, okay? And that's why we've got this publisher ID over here. This particular game, GTA 4, was published by who? Oh, publisher ID 1234. That means I go over to this publisher table, and who was publisher 1234? I look that up by the primary key, and I see that it was Rockstar Games. And by separating those two out, I've normalized the data and I've reduced the redundancy so that, that I only have data in one place. I've separated out these logical units. Now over here, I've got a platform table. A platform could be PC, PS5. What's the current Xbox? Series X? Okay. Why can't they just go in numbers too? Series X, Xbox. Right? Mac, not really though. What else? Oculus, Vive, Rift, say what? Index, right? So a bunch of different platforms. Those are all PC though. So what else is out there? Switch, of course. What? Oh, LS? What's? Oh, Steam OS. Okay, Steam OS. That runs on what? Oh, okay. Steam. Okay, so there you go. I guess you could get. You can get Steam natively on Mac, right? I have it, but
it's just more something that they're coming up with for the Steam Deck.
Okay, all right. Anyway, what would you buy a PS5 if there was only one game for it? No. So a platform should have multiple games. But one game, GTA 4, or the abomination that the 20th anniversary that they released, it's available on multiple platforms. I think it's even available on the Switch, isn't it? Yes? No? All right. It's available on PC. It's available on PS5. Right? You have one game that can appear on multiple platforms. You have one platform that has multiple games. How did I achieve that relationship here? With another table called availability. Here I've got two foreign keys. This game ID and this platform ID. Those are mapping back to this table, and the second one, platform ID, is mapping back to this table. And then I've also got a year published, because it could be that it was released on Xbox in 2015, and then it was released on PS5 in 2017, whenever PS5 came out. I don't know. Right? I'm not a gamer. I don't have any of this stuff. I have an Xbox 360. that has not met with the red ring of death yet. Oh, once it did, but it's still going. So anyway, that's the table here forms a many-to-many relationship between these two tables. Now, what I'm going to do is I'm going to come over here, and using this as a basis, let's think about some scenarios, okay? For example, I want to insert, say, GTA. I guess they were on 5, right? GTA 5, right? Here are my tables. Right? What do I need to insert? Of course, I need to insert a game record here, right? So I'll go ahead and insert it into the game table with a name, with a ID. It'll be auto-generated. I'm going to let the database handle that for me. I'm just doing this conceptually here. I'm not going to show you any SQL. I'm not going to show you how to do this. In your lab, we've written functions for you to do this for you, right? All you have to do is provide the name of the game. GTA 5 or V, whatever it is. Right? Now, is that going to work? What else does a game need here? A publisher ID. So if I'm going to have a publisher ID. Uh-oh. So what do I need to do before I insert a game record? I need to create the publisher first. Or if the publisher already exists, I need to find its publisher ID. Right? So insert or retrieve publisher with name Rockstar Games. I'll just shorten that to Rockstar. Right? And now, if that if I insert that record and it generates a publisher ID, oops, pub ID, I'll shorten that to of say 5 or 4, 3, 2. Right? I'll just make it longer here. Then I can use that when I insert this record, 5, 4, 3, 2. Okay. The order there, it matters. The order is important. Let's go back over here to this diagram here. This one-to-many relationship defines also a parent-child relationship. You have a publisher. This is the parent. And it has many children, right? That one publisher could have GTA 1, 2, 3, and 4, right? These are its children. So in database management systems, we say that you can't have any orphans. In other words, the parent record must exist before its children. Otherwise, if you have a child with no parent, right, you have an orphan, or you have a child born ex nihilo or whatever, right? So there's some Latin for you today, right? Out of nothing. Right? They just popped into existence somehow. Right? So we have a parent-child relationship. So if I want to insert a game record, a child record, what do I need to do first? I need to make sure that that parent exists first. Now, what if you wanted to go in reverse order? What if you wanted to delete a record? What if you wanted to delete, let's go with red here. What if I wanted to delete that Rockstar publisher record? Yeah, what do if I just did that directly, what would I have? A bunch of orphan data. The data would still exist. It's just that, okay, GTA 1, who published that? I go back to the other table. I go back to the publisher table, and I see publisher 5432 doesn't exist. Therefore, I don't know what their name is. Right? You would end up creating a bunch of orphaned records, and we don't want that. So order matters. Creation. The parents have to exist before the children. Destruction, destroy. You have to delete the child records, before you can delete the parent records. Right? Order matters here. Now tell me about the same order over here with respect to game and platform. Can a game exist without a platform? Sure. Right? You don't have to have a record down here in availability. Just like GTA 5 doesn't have to be published on PC. It could just be a PS5 exclusive. Right? Sorry, that's the first game that popped into my head because of the reboot, of course. I don't know what other games are coming out. What's the Pokemon ones? Sun and Stars or something. What is it? Sun and Moon? Okay, there we go. $60 though, right? I've never played any of the Pokemon games, so I don't know. Too expensive. Anyway, can a platform exist without games? Yeah, right. Because this many-to-many relationship includes a 0 or a 1-to-0 relationship and a 0-to-1 relationship. So each game record, can exist without being available on any platform, and you can have a platform, a brand new platform for which no games have been published. So does the order matter there? I create a game versus I create a platform? No. What's the parent-child relationship here? We actually have 2 parents for 1 child down here, right? Versus there's only 1 parent record for this one over here. So if we wanted to make a game available on a platform, we would first have to create the game and then the platform, or the platform and the game. And then after both of those records exist, then we would insert a record into this availability table here saying that this game is available on this platform. Right? So the order matters. What if I wanted to delete a game here? If I wanted to delete a child record, I would have to delete the availability record. If I wanted to delete a game record, would I necessarily have to delete the platform record? No, that sounds even worse. You want to delete the GTA 5 record? Okay, go ahead and delete PS5 because it's available on that. Delete Xbox 360 because it's on that, or whatever. Delete PC because it's on that, right? No, that would end up deleting the platform record for a whole bunch of other records that are unrelated to GTA 5. Right? So, order matters, and you have to be careful about the order. So on your lab next week, it'll ask you to insert your favorite games. You can just make up a game if you're not a gamer. You can see the games that I've put in there, and then you can determine how old I am based on the 20 games that I put in there. And then check those games out because they are awesome. Right? But anyway, you can go ahead and check, insert your own records, but you have to use our code to do it, and you have to do it in the correct order. Okay? Remember that a bunch of stuff is coming due this Friday. Any hack resubmissions, you still have to contact me. Only about 1/4 of the class has done so. So make sure that you're contacting me before Friday and resubmitting it before Friday. Make sure that you are filling out that bonus survey before Friday. That's the due date on that. Otherwise, next week, both Monday and Wednesday, we'll use that as a review. I'll bring old, actually, it's December 1st, right?
Oh, yeah.
We can do that. I'll save it. I won't do it. It's probably the same thing. I don't know. I'm not going to read it here, but you can read it. We can start doing that if you want to, or I can bring an old final and we can do that. We can do as many exercises as we want, both Monday and Wednesday. All right? Any questions? Yeah, go ahead. No, we won't look at those until the due date, December 3rd, Friday midnight. Okay. I'll see you next week then.